Hello, today I'm going to show you how you can create a NetCDF file using R. I'll show you how you can create data variables with either 1 dimension, 2 dimensions, or 3 dimensions. I'll show you how you can write metadata to the file in the form of variable and global attributes. And I'll show you how you can make your NetCDF file compliant with both the climate and forecast conventions to make a CF NetCDF file, as well as using global attributes from the attribute convention for data discovery. A NetCDF file by itself is not necessarily fair. The CF conventions and the attribute conventions for data discovery help provide structure to your file and tell you which variable and global attributes you should be including and how to fill them in. So together this makes the file machine readable and therefore FAIR compliant. In the description below the video is a link to this Jupyter Book. This includes all the code that I'm going to go through today, as well as explanations. And whilst you're down below the video, why don't you go and hit the like and subscribe button for me? So I'm going to open up RStudio now. You can either code along with me, or perhaps you just want to copy and paste code from that Jupyter Book. Before I start, I should say it's raining quite heavily here. I hope that's not coming through too much in the recording. So first let's load in the libraries we're going to use today. So a library. And the library we're going to use is RNetCDF. If you haven't got that installed already, do that below in the console. So install.packages, and then in quotation marks this time, RNetCDF. I've already got this installed, so I'm not going to run this. So now let's start by creating an empty file. So we're going to call it NCDS for NetCDF dataset. And we're going to use a function create.nc from the RNetCDF library. And we can just put any file path in here. So I'm just going to save it to the folder that I'm working in and call it test.nc. But perhaps you want to give it an absolute or relative file path here. And then below this, I want to see what we've created. So we've got this command print.nc. And we're going to print this NCDS object. So let's run both of those lines. And you can see in the console below, we've created this NetCDF file. It's a classic NetCDF file. And at the moment, it's completely empty. So let's start now by creating some data that we can add to this. So I'm going to go above this here. We'll start with a vertical profile of data. We'll call this variable depths. And this is just going to be a list of values. So maybe 0, 10, 20, 30, 50, and 100. So I'm going to run this. And I'm also going to want to count how many depths I have in this array. So I can do that by saying the number of depths is equal to the length of this depths variable. Now below this line, we can add a dimension to our NetCDF file. So a dimension tells us about the shape and size of our data variables. This will become clearer once we've built this up a bit, so just bear with me. So let's define a dimension first. We can do that with dim.def.nc. We need to give it our NetCDF file, which is ncds. Next, we need to assign a name for this dimension. So I'm just going to call it depth. Our dimensions, as I mentioned, tell you about the size of our data. So then we only need to assign here a single value, which is the num depths. So if I run this now and print the NetCDF file again, you can see that this dimension depth has been added to the file. Note that this doesn't currently tell you anything about the values of these depths. They need to be added in variables. And our variables that are associated with these dimensions are called coordinate variables. So let's define one of those. So we're defining the variable here, so it's going to be empty at first, but var.def.nc. See how the syntax is very similar to how we're defining this dimension. This will be a common theme throughout. And this is one thing I really like about this RNetCDF library. So then we give it NCDS, our NetCDF variable. We then need to assign a name for this variable. It's quite common practice for this to be the same as the dimension it's associated with, so I'm just going to call it depth again. These values are then all integers, so we can do nc int. So that tells us what type of values we should expect to have in our data variable. And we need to tell it which dimensions are associated with this variable. So in this case, it's just one dimensional, and the dimension is called depth. So if we run this and we print out again, now we can see in the console, we have a single variable called depth that has a single dimension in brackets, also called depth. And you can see if you called this something else like my depth, for example, which I wouldn't recommend. But just to show you, then you would have a separate variable here, a variable name, and a dimension name here. Now, we don't want that, so I'm going to run all of this code again. So we've defined our variable, but we haven't actually put any values into it. So we can do var.put.nc, the name of our object, NCDS, depth, which is a variable we want to write values to, and our variable up here with the values is called depths. Rerun that. Now, you don't see the values within this print.nc, but you can do something like, maybe I'll just do this in the console, var.get.nc, NCDS, which is the name of our object, and depth, which is the name of our variable, and you can see the values are written out. So integers aren't the only type of values you can write to your NetCDF file. I'll show you this from the NetCDF documentation. You can see there's lots of different data types. So there's NC_char for if you want to represent text, NC_byte for 8-bit integers, NC_short for 16-bit integers, and NC_int for 32-bit integers. So actually, if your numbers are small, you might want to go for one of these two. You have NC_float for 32-bit floating point values. That's numbers with decimal places. And NC_double if your floating point values have a lot of digits. In most cases, NC_float will be okay. There's some other formats here. One that I will mention is this NC_string. So if you do have a variable which is a lot of different character strings, and they're all of different length, then it's better to use this than using this NC_char. I'll put a link to this documentation down in the description. One thing you might have noticed is that there's no kind of date time or timestamp format here, and that's because of the way that times are usually encoded within NetCDF files, or how they should be encoded. There's a good description of this here, and I'll put a link to this page in the description as well, but I'll briefly try to summarize. So if we go back to the RStudio, we'll make a bit of space. We can write the data to the same file for now. Let's say we have a list of timestamps. I'm just going to copy in some code that I wrote earlier because this is just dummy data. But if you have a look at this value, you can see that you have all the timestamps here. They're all on the same date, and there's a 3-hour time interval. Now, one question you might have is why can't you just write this long character array for each variable? Well, there's two reasons. Firstly, if you have a really long time series, this can be quite inefficient. This can take up quite a lot of space. The way this should be done in NetCDF instead is you assign some units, so something like seconds since some time. So this could be from 1970 0101 T 000000 and Z for UTC time, so plus 00 hours. And then all of your values would be something like 1, 2, 3, 4, whatever. And they don't have to increment. You could also go 4, 6, 12, and they could be decimal numbers as well, so 13.4. So in writing your time values like this, it also means that your times are stored with numerical values, which is the same way that other coordinate variables should be stored. So that makes it easier for software to read and understand the values. And it doesn't have to be seconds since 1970, blah, blah, blah. It could also be days since, or maybe even years since. And it can be from any time you like. So this could be from 2022, for example. It's quite common to use the 1st second of 1970 because this is then a Unix timestamp. It should be seconds in this case, but it doesn't have to be. I'd recommend against using months, for example, because this can be ambiguous because of the different lengths of each month. But seconds, minutes, hours, days should be okay. Now, the thing is, your data are usually in timestamps. So how do you get from timestamps like this into some numerical values in the units, for example, seconds since some date or days since some date? Well, let's do that. I'm going to get the data into hours since this first timestamp. I'll remove these 2 lines that I don't need. So I'm going to work in the console first to show you how to build this up. You can find the difference between 2 times using a function called diffTime. So then we can provide 2 different times. I'm going to provide the second time in my timestamps value. So I can do that like this. And the difference between that and also the first time. And if I run this, and I've made a mistake here, I think this needs to be actually double square brackets. And I run this again, and we see time difference of 3 hours. We can actually specify the units as well. So if we want to do here, units equal hours, which is what we want. But this could be in seconds, as this is what we're waiting for. Sorry, that should be secs, apparently. Or any of these here. Now, at the moment, this value is just a character array. Now, at the moment, this value is just this character string, but we want our values in integers. At least I want the values in integers because this is all going to be integer values. You might want your values in floats, for example. So then I can do the same again, but then I'm going to embed all of this within this function as dot integer. But we don't want to do this just for each value one by one. Instead, we want to find the difference between all of our values and the first value in the list. So then we can use this function called sapply, which allows us to apply a function to a whole array. And the array we want to apply this to is timestamps. And then we go function ts. So that means I want to make each value in turn equal to ts. And then I do a space, copy and paste this. But we need to edit this a little bit. So in this case, we don't want to just use a single value here. We want to undo all this and make this equal to this ts value. Now we'll try and run this. That looks good, but I instead want the units to be hours in my case. So let's add this to our script now. Copy and paste it up here. We can call this time diff hours and make this equal to this. But let's go and write this data to our NetCDF file. We need to define a dimension first, dim.def.nc. NCDS is our NetCDF object. We're going to call the dimension time. And this needs to be equal to the number of times in our time series, so we can go length time diff hours. We can then define our coordinate variable for time var.def.nc NCDS. We're going to call our variable time. All these values are going to be integers in my case. You might do NC float if you have decimal numbers. And this variable is going to have a single dimension, time. Finally, let's put the values into that variable var.put.nc NCDS. The name of our variable now is time, and this time diff hours list. Let's have a look at the NetCDF file, and we've added this time dimension and time variable to our existing NetCDF file. You might have different coordinate variables, latitude, longitude, for example, but you can follow the same pattern as you did here. Just remember that your latitude and longitude should be in decimal degrees. So we've written our coordinate variables. Let's go and write some data variables now. I'm going to clear up this script. We can keep our depth variable and dimension. But let's start by writing a one-dimensional data variable to our file. So we need to remember that the number of values in our data variable need to be the same as the number of values stated by this dimension that you're associating with the data variable. So I'm going to create a data variable below here called chlorophyll A, for example, and I'm going to give that 6 values, just something random here. I'm going to run this through a bit so that we create a blank NetCDF file. We can again write our depth, dimension, and variable, and we can define our data variable in exactly the same way as we defined our coordinate variable. So, nice and easy, var.def.nc, NCDS. The name of our variable, we'll call it chlorophyll A. These are decimal numbers, so I'm going to call it NC float. And this is a vertical profile of values. The single dimension is depth that we've defined here. So depth. So if we look at that now in the console, we can see we've added a variable called chlorophyll A, and in brackets, it has a dimension of depth. And let's go write our values then. var.put.nc.ncds. We're writing the values to this chlorophyll A variable. And our variable that we want to write, our R variable, is chlorophyll A. So that's quite straightforward, I think. So now let's move on to something a bit more complicated. What happens if we have a regular two-dimensional grid of values? I'm going to delete all of this. I'm also going to delete these values here. So we're left with just loading in the library, creating an empty NetCDF file, and printing out how that looks. Now I'm going to define some values. So let's say we have some latitudes. And I'm just going to assign some random values here. And we might have some longitudes as well, so something like this. So we have 3 points of latitude, 2 points of longitude. So I'm going to go ahead and define the dimensions, the variables, and write these coordinate variables to the file. So something like this, I'm defining both dimensions, defining both variables, and writing the values to those variables. We then need a two-dimensional array of values. I'm going to create some dummy data now, but I assume you will have real data. Let's say we have some wind speed values, and I'm going to use this function called runIf. What this is going to do is create a list of random values. So I want this list to be 6 values long, because it's 2 by 3. And let's have the minimum value to be 0, and the maximum to be 10. It really doesn't matter for this tutorial. You can see the values here in the environment, but if we look at the values in the console, we can see that this is just a one-dimensional list. So we need to reshape this to become a two-dimensional array. So let's update this, wind speed, and we're going to make this an array. Take the wind speed values. We're going to assign the shape using this dim argument, and this is going to be a list. And we could write here 3 and 2 for a 3 by 2. Or we can do it more dynamically and say make this equal to the length of our latitudes array, and make this equal to the length of our longitudes array. So up here, if we look in the console now at those values, we can see we have a 2 by 3 array. Let's go and define our data variable now. So we can do var.def.nc, NCDS. Let's call it wind speed. These are going to be decimal numbers, so NC float. And this all looks familiar so far, but here's where it gets different. Now we need to assign a list of dimensions. So C for a list, And the two dimensions we want to provide it with are latitude and longitude. And that order is important because here we assigned latitude first and then longitude. So in quotation marks, because it's the name of the dimension, latitude and longitude. Let's have a look at how that looks in the file now. So now you see we have this wind speed variable, and it has two dimensions. And then writing the values is just the same as we've done before. var.put.nc, NCDS, the name of the variable, and our values. This is actually an advantage of NetCDF files over other, for example, tabular file formats. If you have a table like a CSV file, you're kind of restricted to one dimension. Whereas in NetCDF files, there's really no upper limit to how many dimensions you can have. The data will be stored in a multi-dimensional array, and so they're ready for someone to use without them having to reshape it themselves later. We can have a look at that. var.get.nc, NCDS. Let's have a look at our wind speed values. And there we go. Now, if we had to find our dimensions in the wrong order, so for example, if we had a longitude here and a latitude here, what would have happened then? Well, if we run all of this, you see that it's been defined okay, but then you have this error in this line here, var.put.nc, and this tells you that the bounds of the dimension have been exceeded. So that's good. If we do make a mistake, which is easy to do, it's easy to write the dimensions in the wrong order, at least the code will fail and there won't be any problems. Of course, you have to be a little bit careful if you have dimensions of the same length. So now what about a three-dimensional data array? So first, let's clean up this script. We don't need this data variable anymore. We can keep this for latitudes and longitudes. But let's say we also have some depths, something like this. Now I'm going to create some seawater temperature values. Seawater temp. I'm going to use this run if command again to add some random values. And the length of this is going to be equal to the length of our depths variable multiplied by the length of our latitudes and multiplied by the length of our longitudes. Something like this. Well, let's assign some values. Minimum is 0 maybe, and max 2. It can be cold water. And again, I'm going to reshape that array. So seawater temp is a function array, seawater temp, and the shape with this dim argument is going to be equal to a list, and this is going to be the length of our depths variable here, the length of our latitudes variable above, and the length of our longitudes variable. We run that. Let's have a look in our console to see how that looks. And there we are. So I'm going to go ahead and define the dimension and the coordinate variable for depth and write the values. And here we are, something like this. And then let's define our data variable, var.def.nc. We're going to call this seawater temperature. Oops, I've forgotten NCDS at the beginning for my NetCDF file. These are going to be floating point values. And the dimensions, we need to go back here to get the order, depths, latitudes, and then longitudes. So, C for a list of dimensions, depth, latitude, and longitude. Let's go and put those values in as well. the name of the variable. And what did I call it? Seawater temp. And we'll write those values, print that out, and you can see the variable has been written here. I'd also like to quickly show you how you can get the data into a three-dimensional array if your data are in a data frame. I know many of you might be working with data in tables. So I'm just showing the head, the first 6 rows of this data frame. So how do you go from here? Well, actually, it's very similar to what we've done before. In fact, I can copy and paste the relevant line across this array. So to create a three-dimensional array of our salinity values, we can call this salinity 3D, for example. But instead, this time, the array that we want to reshape is one of the columns in our data frame. So we can go data, which is the name of our data frame here, and we can call that column. So a dollar symbol and salinity. If I run this, we have a look at our salinity 3D values. We can see it looks like this. And then you can go write them to your NetCDF file in the same way that we did just previously. Now, I've only discussed regular grids of data here, but if you have an irregular grid of data, or perhaps you have an instrument that's moving and recording every second or whatever, I'd recommend that you create a NetCDF file with just a single dimension, time, and you allow a latitude, longitude, and a vertical value, if relevant, to be one-dimensional data arrays using time as their dimension. And this is a very efficient way to store the data. If you try to do something with multiple dimensions, you end up with a hell of a lot of empty space in your file. So let's keep this simple. We're going to go back to our first example now, and it's time to add some metadata. Now, metadata in NetCDF files can be broken down into variable attributes that describe each of our variables, and global attributes which describe the file as a whole. It's things like who the authors of the file are, the title, things like this. So let's scroll down here and let's write an attribute to our depth variable, this one here. We can do that. We just do @.put.nc. See, the syntax is similar again. NCDS for our object. Then the name of the variable we want to assign the attribute to. So let's go depth. And then, as we can see in this yellow box, the next argument we need to give is the name of the attribute, then the type of attribute, so the data type. Mostly it will be a character string, and then the value of the attribute. So in a NetCDF file, you could assign any variable. So something like my variable, let's say NCHR for characters, some words, and some variable like this. And if I run all of this, we can see now in the console that this depth variable has now a variable attribute assigned to it called myVariable, and this is the value. Now, this particular variable attribute is obviously useless. It doesn't tell us anything. And this is where the conventions come in. So this is the CF conventions document, the climate and forecast metadata conventions. And this is version 1.11. New versions are released approximately every year. And this is a long document. It's about 262 pages. But of course, you don't have to read it all. And I'll navigate you through some useful parts of this document throughout this video. So there are 9 distinct sections, and then a lot of appendices as well. And the appendices are actually now about the same length as the main document. So if we have our vertical coordinate, our depth coordinate variable, we have this section here on coordinate types. We can go to the vertical height or depth coordinate section, and it tells us what variable attributes we should be including and how we should fill them in. So for example, we need some units, and it's suggested meters here, but it could be something else. And you should also have this variable attribute positive, which tells you whether your vertical profile is going upwards or downwards as values increase. Also, every variable in our NetCDF file should have a standard name attribute and a long name attribute, according to the CF conventions. The long name is our own description for what that variable contains in free text, and this can be as long as we want it to be, whereas the standard name is the standardized name for that term taken from the CF standard name vocabulary. So we have this CF standard name table here, and it's searchable. So if you wrote something like depth, you can see that there's a depth standard name with a description associated with it, and there's some canonical units. You don't have to store your data with the units of meters, but they should be physically equivalent to these canonical units. So it should be meters, kilometers, centimeters, but it couldn't be, for example, degrees Celsius. For other depths, you could include perhaps depth below sea floor or depth below geoid, but in our case, we're just going to take depth and keep things simple. So let's return to R now, and we can get rid of this, and we'll replace this with standard name. We're going to assign a standard name of depth. I'm going to copy and paste this for our second attribute, which is going to be a long name. And it's not uncommon just to have a long name that's also depth. You could perhaps also put depth below sea surface or something like this. We're going to define some units as well. And these units should be something that's recognized by the Unidata UD units package. Don't worry too much about that. When we run it through a checker at the end of this, it will check that our units are actually UD units. Let's return to R again. Now we should remember as well that we have this other attribute we need to assign, positive, and given that our values are increasing as we go down below the sea surface, this should be down. The attribute convention for data discovery is mostly the global attributes you should be including. However, there are also some highly recommended variable attributes. The first three are recommended by the CF convention, long name, standard name, and units. But we have this other one, this coverage content type, and this is to tell someone using the data whether these values are coordinate values, or physical measurements, or perhaps output from a model, or something else. These are ISO 19115-1 codes, and if you want descriptions for what each of these terms mean, you can find this on this page here, and I'll provide a link to this in the description as well. So for now, we're going to do coverage content type and make this equal to coordinates. The CF conventions defines a lot of other variable attributes you can be including. In fact, in this Appendix A, it's not just variable attributes. You can see whether the attribute is to be used as in a coordinate variable with C, a dimension with D, or for global attributes with G. And there's a lot of different things that you should be using here. For time, for example, you should be including the calendar. You might also want to mention what the valid max and valid min are, which is the largest valid values for that variable. And there's a lot of other things that you can mention within here. I'm not going to go through all of those now. So this is going to be quite similar for all the rest of the coordinate variables, so I'm going to go and fill this in now. And there we go, I've added some variable attributes for the latitude and longitude coordinates. Just remember that in the CF documentation, there's also information on how to encode data with latitude coordinates or longitude coordinates. It tells you what the long name could be in the units and the standard name. It also has a section where it talks about time, discusses what I mentioned earlier, and it's very important that the units are encoded in this very particular way. It could be days or seconds, space since, and then from your timestamp. And this timestamp should be in ISO 8601 format, which is something like this for UTC time. And generally, I think it's best practice to store the data in UTC time rather than some local time. But I'm sure there's exceptions to that rule. We could do something similar now for the seawater temperature, which is our data variable in this case. So I'm going to copy this and I'm going to paste it below. And I'll just do some updates off screen. So I've added a standard name, seawater temperature, that I've taken from this list here. There's a lot of different seawater temperature standard names. I've used the relatively generic one here. So make sure you choose whichever standard name is suitable for you. If you can't find a specific standard name for your data variable, it is possible to propose one. This can be done on GitHub. The CF Conventions is an organization on GitHub, and they have this vocabularies repository. You submit an issue. You can see a lot of existing issues here. I won't click up on any of them in particular, but you propose a name and a description for your standard name and what the units would be. This is discussed by people who govern the CF conventions and anyone else who wants to contribute. And eventually the new standard name can be added so that anyone can use that. There are some guidelines for the construction of CF standard names. They can't just be named whatever you like. When you get quite familiar with looking at them, you see that there is a pattern to how they tend to be written. Also in the descriptions, I won't go through this here as this is quite specialist and probably not of interest to most of the people watching. So as well as a standard name variable attribute, I've proposed a long name, some units, and a coverage content type, which I've added as physical measurement. And we can see this below now. So now we've added all of our variable attributes, it's time to add some global attributes that describe the file as a whole. So the syntax for this is almost exactly the same. @.put.nc, NCDS, our object. And instead of a variable name, we're just going to write nc_global, which is like a special type of variable name just for global attributes. Then we can include a attribute name, for example, title. This is going to be text, so nc_char, and whatever the title is going to be. And the title should be quite descriptive. And remember, this is the title of your data set. It's not the same as the title of your paper. You should really try and separate these two things in your mind. That someone who's looking at your data might not necessarily be looking at your paper. So the title of a list of authors on your data set does not necessarily have to be the same as the list of authors of the paper. So on the CF conventions page, there's a list of different attributes as I mentioned, and some of them are suitable global attributes. So you can go and look through here for what might be useful. I also touched upon the attribute convention for data discovery. So the CF conventions are quite light on discovery metadata. Discovery metadata is metadata that helps someone find or discover a dataset. So this is why we often use the attribute convention for data discovery on top of the CF conventions. So we can go to the global attributes here. There's some highly recommended attributes that everyone should be including, some recommended attributes, and some suggested attributes. Now, where I work at the Norwegian Meteorological Institute, we have a data center, Arctic Data Center, and then we have certain requirements. We believe that requirements are a better way to promote consistency between data sets than recommendations are. And these are good requirements. They're not specific to Arctic data or anything like this. So you're very welcome to come here and see what requirements we have. This is all based on the ACDD conventions and the CF conventions. And I'll put a link down to this in the description for those of you who want to be following these requirements. So let's return to R now. So here I've shown you how you can define attributes one by one. You can just add a second line to define a second attribute. If you'd rather define them in bulk, you can do it like this using a list. This is something I prepared earlier. So you have a list of attributes which are pairs, which are key value pairs of attribute and their value. And you can go through and look at this if you like. This is also in the code in the description. And then if you want to write each of these attributes in turn to your NetCDF file, you can do that using a for loop. So a for loop is going to help you loop through a list of values. So for key in names attributes. So that's saying for every key in this attributes list, then in these kind of funny curly brackets, we can do something for each loop of this for loop. So for example, @.put.nc, NCDS, nc underscore global for the global attributes, the key, which is the attribute name. All of these are going to be nc char in this case. And we can do then attributes, which is the name again of our list, and in square brackets, key. So that will call the value for the respective key within that list. But don't take my word for it. Let's have a look at how that looks. Looks like I've made a little typo here. This key has to be actually double square brackets. If I run this again, and now we can see a load of global attributes at the bottom of our NetCDF file. Now, here we've only defined the attributes that are all in nc char format, but some of the attributes are going to be numerical. So, for example, the bounding box of your coordinates. So we have all of these geospatial global attributes. What I definitely recommend is the geospatial lat min, geospatial lat max, geospatial lon min, and geospatial lon max. And if your data are spanning some depth range, it's also nice to have geospatial vertical min and geospatial vertical max. Why are these important? Well, these will define how your data are going to look on a map. If someone's looking for your data in some search portal, perhaps at the data center, a potential data user isn't going to be able to see each location that's been sampled. This discovery metadata provides a bounding box for your coordinates. So it'll show up as a bounding box on a map. So let's go write those as well. I'll just scroll down a bit so we can see better. Hat.put.nc, NCDS, NC global for a global attribute. Let's call it geospatial lat min for the minimum latitude. This is going to be a decimal number, so NC float. And actually we can derive this from what we've written earlier. If we go up here, we've already provided the list of latitudes in the file. So if we go back down again, we can just do min latitudes. And we could do something similar for the maximum, like this, and also for the longitude values, like this. I'd also recommend you include this date created variable, which is the date on which this version of the data was created, and also the history, which is like an audit trail for modifications to the data. And the reason I'm talking about this separately is because I can show you how you can take the current time and encode that within the file. So if we look in the console, we can do sys.time, and that will tell us the time right now. So that means we can write this to a variable we're going to call dt now, make that equal to this sys.time, and we want the time to be in UTC, so plus 00 hours. We can do that by going atra dt now, tzone for time zone, and UTC. So if I now type in dt now into the console, we can see that this is 2 hours earlier. Now this should also be in ISO 8601 format, so we can do that. We can go dt8601, which is what I'm going to call my variable, and we're going to format this dt now value. We're going to provide a string that tells us how this date time should be encoded. So we have this % symbol and a capital Y, which is for 4-digit year, month, day, capital T, hours in 2 digits, minutes in 2 digits, and seconds in 2 digits, followed by a capital Z, which means UTC. So let's have a look at that. And if I look in the console at how this looks, there we are. And then we can simply write this to our global attribute. So NCDS, NC underscore global. The attribute is date created. The type is NC char because this is now a text. And the value is this 8601 variable here. And there we go. And the history is going to include this text. So I'm going to write history here, and I'm going to paste together some different bits of text to make a single text string. So we can do paste, file created at, and they're going to put a comma, DT8601, using our NetCDF by me. Then we can write that attribute as well, and there we go. So there's the file created. The last thing now is to check that it looks okay. You should be doing a sanity check in the console yourself, making sure that each of these variable attributes looks okay, making sure the global attributes looks okay, perhaps checking some of the values as well. And just like with any other publication, if there's a list of authors, you should be giving each author the opportunity to review the file before you publish it. Now, we humans are prone to overlooking typos and things like this, so this is why CF checkers are very useful. So I'm going to recommend one here, the IOOS compliance checker. You can check it via the version of the conventions that you have encoded your data to. Currently, this only goes to CF 1.8. It could do with a bit of an upgrade, but you can check it first against ACDD conventions. Upload your file. It will spit out some warnings or errors if there's anything that needs fixing. And you can do the same for CF and whatever version is the latest version available. Also, if you have a friend or colleague who perhaps knows a little bit more about NetCDF than you do, feel free to share it with them. Perhaps you have a data manager you can ask. The compliance checker is useful, but it isn't as thorough as it perhaps could be. And so it's always nice to run this past another pair of human eyes before you can publish your data. I'm going to end this video here. I've included everything that you should need to get on with this in the description to the video. If you found this useful, please like and subscribe to the channel. Drop me a comment to say what you thought about the video. All these things really help the YouTube algorithm and helps more people find these videos, which ultimately helps more people publish their data. I'll see you next time.